last bit of the binomial theorem to look at, and this is this idea between finding relationships between all the different binomial coefficients. Remember, binomial theorem. Every one of these questions, basically if you start off with the binomial theorem, and then you can't go wrong. You just start with it and go, how do I manipulate this into what it is I'm trying to show? And remember the binomial theorem in sum notation, NCKX to the k, so that's our general term. K is going from 0 to n. Sometimes it's useful to write the whole thing out to pick up on patterns, and so NC0 or NC1x and so on and so on. Somewhere in the middle I just put the general term, and then at the end the last one would be NCnx to the n. Find the values of k going 1 to n of nck. So if I was to add up all of those particular coefficients, what would they equal basically? So I start, well there's the binomial theorem. Have a look at the sum I'm trying to prove, have a look at the binomial theorem. You'll notice there's no mention of x there, so we're going to have to do a substitution for x. What would be a logical substitution for x? So I would end up with just nck and not nck x to the k. Yeah, 1. Because 1 to the power of anything is 1. So we'll let x equal 1, and now binomial theorem says 1 plus 1 to the power of n is the sum of k equals 0 to n of nck. Close to what I want, but not quite the same. So 2 to the power of n will be k equals 0 to n. Well, all I've got to do is take away the term where k equals 0, and I've got my answer. So the term where k equals 0 would be nc0. nc0 by definition is always 1. So subtract that from both sides, and I've got my answer. The sum from k to 1 of n of nck will always be 2 to the power of n minus 1. Okay. What about if I want to know what all the odd ones add up to? So I'm interested in all the odd ones. So again, I'll start off with my binomial theorem. Well, we just saw that if I substitute in 1, I'll get all of them, odd ones and even ones. So this is where I'm going to actually write the whole thing out to try and see how am I going to get the odd ones. So if I let x equal 1, then I'll get 2 to the power of n is nc0 plus nc1 plus nc2, and so on and so on and so on up to the very last term. Now that in itself is a good result. What that's basically saying is any row in Pascal's triangle will always add up to be 2 to the power of n. Okay. If I now let x equal negative 1, then we're going to alternate plus minus, plus minus, plus minus, plus minus on the right hand side, which will create simultaneous equations. I've now got 0 on the left-hand side, but I've got nc0 minus nc1 plus nc2. So by either adding or subtracting those two results, I can be left with either all the even ones or all the odd ones. Now in this case, they want all the odd ones. So I want to be left with the odd ones. So if I subtract them, on the left-hand side, 2 to the power of n minus 0 is 2 to the power of n. nc0 minus nc0, so that one disappears. nc1 minus nc1, so I've got 2 lots of nc1. nc2 minus nc2 disappears. So all the even ones will disappear, leaving me with 2 lots of all the odd ones. So if I divide by 2, I get my result. So 2 to the power of n minus 1 will be all the odd coefficients added together. All right, k nck. So in other words, that would be 0 times nc. Oh no, we're starting from 1. So it'd be nc1, 2 lots of nc2, 3 lots of nc3, 4 lots of nc4, and so on. So again, let's have a look at our binomial theorem. What mathematical operation could get that power of k and put it in the front? Differentiation. So if I now differentiate both sides, this is where sum notation can be useful because I don't have to write out every term. I can just get the general term and say, well, this is what's going to happen. So if I differentiate both sides, left-hand side, I'll get n lots of 1 plus x to the n minus 1. On the right-hand side, I get this new general term, k nck, x to the k minus 1. And so now I can let x equal 1, and that will leave me with the k nck that we're looking for. So on the left-hand side, I've got n times 2 to the power of n minus 1. It's going from 0 to n. We want 1 to n. But actually, the term where k equals 0 is 0 anyway, so it actually didn't really matter. But I suppose I should mention that. So, because if I just went equals 1, it'd be like, well, hang on, how did you just jump from k equals 0 to k equals 1? So I need to explain myself there that, hey, that first term is actually 0 NC0, which is 0. And we get the relationship that we want. Okay. Well, again, there's the binomial theorem. This time, I want k plus 1 on the bottom of the fraction. What mathematical operation will do that? Yeah, so it's now the reverse way, because we'll add 1 to the power over that new power. So if I integrate both sides, now this is where we've got to be careful, because whenever people integrate, what do they forget? Plus a constant. So I'm going to add plus a constant. I've used capital K for constant, because if I used C, I could get confused with NCK. If I use K, oh, hang on, K is already there, so I went capital K. I mean, it could be any pronumeral, really. So add 1 to the power over the power. Right-hand side will do the same. I'm going to have to work out what that constant of integration is, though. And I'm also comparing my general term. What's different in our general term to what I've got? Yeah, so logically, we'll do a x equals -1 substitution as well. So which way did I go first? First of all, I'm working out the constant, because if I let x equal 0, then every term in the right-hand side is going to be 0. So I'll sum them all to be 0, and I can work out what this capital K is then. So the right-hand side is all 0. K ends up being -1 on n plus 1. If I let x equal -1, okay, so the right-hand side, that's getting very close to what we want. They've got power of k plus 1. We want power of k. That's easy to sort out because we're playing with 1 and -1. Left-hand side, we've made capital K equal to -1 on n plus 1. 1 minus 1, oh, well, that's 0. So, that's almost it. K equals 0 to n. The powers are different. How can I turn power of k plus 1 into power of k? If we divide both sides by -1, then I'll have -1 to the power of k. And so the right-hand side will become +1 on n plus 1. So all of these ideas playing with the first step is write down the binomial theorem and have a look, compare, well, how can I manipulate this general term into what they're looking for? This is probably the most fun of them all, is when we start comparing coefficients on both sides. So we've got this expression, 1 plus x to the power of n times 1 plus x to the power of n, which of course is the same, or congruent, which just means identically equal to. Don't worry, it's not geometry, it's just, it is the same symbol. 1 plus x to the power of 2n. And we're going to show that. Remember, that's our alternative notation for NCK. So all of the coefficients squared, when we add them together, will end up being 2n factorial over n factorial squared. So there's our binomial theorem. Well, they've given me a hint on how to do it by comparing coefficients on both sides of the identity. So I'll write the whole thing out so I can get a feel for this. So I want to look at the coefficient of x to the power of n, first of all on the left-hand side. I've got 1 plus x to the power of n times 1 plus x to the power of n. So it's this expression, nc0 plus nc1x plus nc2x squared, all the way, times itself. I just want to pull out the ones that will end up with x to the power of n. So nc0 times nc0 nc0 in the first parentheses, to end up with x to the power of n, would have to be multiplied by ncn x to the n. So I know those two will match up. So I'll end up with NC0, NCN, x to the power of n. NC1 would be multiplied by the NCN minus 1. So those two will match up. And we can keep doing that matching all the way along. There's nice symmetry about it. And so we'll end up with something like this. So all the coefficients, because of course x times x to the n minus 1 is x to the n, x squared times x, so it's all x to the n. We're interested in the coefficient, so it's NC0, NCN, NC1, NCN minus 1. It's very close to what I want, but not quite there. But remember, it's symmetric, Pascal's triangle. NC0 is the same as NCN. NC1 is the same as NC minus 1, and so on all the way down. So I could rewrite that as NC0 squared plus NC1 squared. And so I have, on the left-hand side, the sum of all the coefficients squared. Okay. So that was one half of what we're trying to prove. So it said by comparing coefficients on the left-hand side and the right-hand side. We've just looked at the left-hand side. That was our coefficient of x to the power of n. Now let's look at the right-hand side, which is a lot quicker. Because it's simply 1 plus x to the power of 2n. So if I was to expand this one out, I'd get 2nc0, 2nc1x, 2nc2x squared. Somewhere in the middle there, there'll be a term that says 2ncn x to the power of n. And it's the only term in that expression that'll be x to the power of n. So on the right-hand side, the coefficient is that one. Therefore, they must be equal, because we said those two expressions were equal. So it's going all the way back, I guess, to what we looked at last year. Remember the idea with quadratic identities, and we said the coefficient of x squared must equal the coefficient of x squared. The coefficient of x. It's the same idea. Coefficient of x to the power of n must equal the coefficient of x to the power of n. So we know they're equal, so therefore there's our proof. Isn't that lovely? Anyway, we haven't quite got to what they wanted. Remember, they didn't say 2ncn. They said 2n factorial n factorial squared. So we've got to take it back to factorial notation. It would be 2n factorial on n factorial times n factorial, which is, of course, 2n factorial on n factorial squared. Okay. Now, in the handout that I gave you, there's a couple of worksheets in there. You might like to go through that. It sort of leads you through some of these same ideas as well. And then, of course, there's the exercise as well.